Okay, we're back with fluid statics for our final section. And in chapter 3, we're going to talk about the stability of objects that are either floating or immersed. So section 3.7 is our final chapter, or final section in this chapter, and then we'll be moving on to chapter 4. So we've got a lot of ground to go through here: pressure measurements, forces on panels, and so forth. We talked about buoyant forces in section 3.6, and now we're in our final section, predicting stability of immersed and floating bodies. And this is important for the design of ships and buoys. A great example of this is this cruise ship that ran aground a couple of years ago off the coast of Italy, and took on some water, and then it didn't sink, but it ran aground, and it was quite an effort, an engineering effort, to get it floated again to where it could be towed and be repaired or demoed. So for immersed bodies, if we look at these, which one of these is unstable and why? So we've got a situation here where we have the center of buoyancy is actually above the center of gravity. In this case, the two are coincident. Center of buoyancy is at the center of gravity, and remember, the center of buoyancy is the location of it's the centroid of the displaced fluid. And in this case, we have a situation where the center of gravity is kind of up and to the right of the center of buoyancy. So I think it's pretty obvious that condition C is the one that's unstable. And in fact, this is unstable over here. This condition is stable. But what's interesting is this condition here in the middle is actually what's called neutral. 1 second, spell neutral correctly. And this situation in the middle, in case B, this object could rotate freely if it's either a cylinder or a sphere. It could rotate, and these things would be unchanged. In this case, there will be a righting moment on this object to obviously pull it back down and make it look like this. Since in these two cases we have a weight, so it's pretty obvious just from looking at these. Now note that these are immersed bodies; they're completely under the water. The situation's a little bit more complicated. Okay, let me just summarize this. So for an immersed body, if the center of buoyancy, C, is above the center of gravity, then the body is stable. If they're coincident, it's going to be neutral. And if C is below G, then we've got an unstable body. So for floating bodies, the situation is more complicated, and we have a more difficult time understanding whether or not the floating body is stable or not. So the question is this ship stable? It turns out that in fact it is. Once it heels or tilts, heel is a word for tilt. Once it tilts, as we can see by this line AOD, once the ship tilts, the center of buoyancy is going to move outward from the center of gravity. We'll see that in a minute, in a better figure in a minute. And thus it produces a righting moment on the ship. And so the ship, if the conditions are met, then the ship will return to its equilibrium position. Obviously, this is important because ships do heel and tilt a lot as they go through ocean waves, because the surface is not typically rough and not smooth. And ships typically have these characteristics where they can take quite a bit of heeling and not become unstable. Basically, the riding moment acts to counter the heel. It will act to turn the ship back in this direction, up in this direction and down in this direction. The buoyant force, as we can see from C, is always acting upward, while the weight acts downward. So these two things produce a torque to the riding to try to keep it in the upright position. So how do we describe, or how do we determine whether a ship is stable or unstable? It turns out that we do that through what's called the calculation of what's called the metacenter and the metacenter height. It turns out that the metacenter height is not shown here, but it's GM. The distance from here to here is the metacenter. The metacentric height, and if that distance is positive, then the ship will remain stable. Obviously, if you heel this thing over so much that M moves down this line and becomes negative, GM becomes negative, then we've got a major problem, and the ship will become unstable and it can turn over. We certainly do not hear very much of ships capsizing. I don't know if you've ever sailed on a small sailing boat, but they're actually, a sailing ship is actually quite easy to, at least a small one is quite easy to tip over. And so let's go ahead and look at how the steps necessary that the book goes through for actually, or the book describes for how to calculate this. So the steps will be to find this distance C prime, which is the lateral displacement of the center of buoyancy. So if we go back to the figure, we're going to be focusing in on finding this distance right here. And our primary goal, of course, is to use that information. You can see that we've got a nice right triangle there, C prime and M. Once we're able to find C prime, that will allow us to through some simple geometry, trigonometry, find the height GM, which is what we want to determine. And again, if this is positive, we're in good shape. If this distance becomes negative, we're in bad shape. So that's what we're going to do. And the second step, as I mentioned, is to just use simple trigonometry. So let's just get going on that. What we do is we use we calculate the moment of inertia. And let's get rid of this here. We calculate the moment of inertia about the origin point there. And so we have this equation for how to do this. Delta V sub I. And so X bar is really just this length C prime that we're interested in. This is the lever arm of the displaced volume. V is the total displaced volume. This is the total displaced volume. And that basic moment of inertia we can find by equating it equal to these differential elements. So X sub I is just an incremental moment arm. It's a moment arm for these little incremental volumes, which we're going to look at in a minute. So if we're able to basically determine these little volume elements, and these are incremental volumes of the displaced fluid. Incremental volumes. So you can see what we're going to be trying to do. We're going to be trying to we're going to be using dA here we're going to be defining dA. It's going to be, in this particular situation for this geometry, it's going to be a function of the little differential volume is going to be a function of this area and also the distance from this point. And again, x bar is equal to C prime, and that's what we're trying to find. So we're basically calculating the left hand, or the downward torque here and the upward torque here, the writing to right the ship. So so let's proceed and do this. The book makes the point that, let me go back. The book makes the point that this entire moment of inertia is equal to the moment before the heel. Oh. The moment before the heel minus the moment of the volume, that the triangle on the left, or the volume, I should say the volume on the left. It looks like a triangle in our figure because it's two-dimensional. And then it's plus the moment that it's going to have this positive moment of this volume, EOD, on the right. Now, they do some kind of mathematical trickery. They mentioned that before the ship heels, this term actually goes to 0. And so that drops out. But they rewrite this equation into equation form instead of just words here. They rewrite it as this. And the minus sign goes away because of the sign of x is opposite onto both sides of that origin point. So we actually end up with two positive terms. That was a little mathematical trickery there, but we're ending up with this. So what we need to do is calculate these two things. The book does a pretty good derivation of this. I'm not going to go through the details of it. You can look in the book if you're interested in more of the details. But basically, through some trigonometry, you can see that it's a pretty easy thing to figure out the volumes and of these little differential volumes and areas. And so what it turns out to be is just the integral AOB on the left side, x squared tangent alpha dA, plus the integral over EOD, the other triangle on the right-hand side, x squared tangent of alpha dA. That's an alpha. And so the book also makes the point that this can be combined in, these integrals can actually be combined into an integral about the water line to find the moment of inertia about the water line. And so this becomes, and tan alpha is in fact, can be removed from the integral. So we end up with this, we're going to look at the area about the water line, and the integral is just x squared dA. Now, if you remember from a couple, I think it was maybe a lecture or two ago, this looks very familiar. This is again the area moment of inertia. So this quantity here becomes what is given, the symbol in the book is given as just I00, which is the, I'll write it down here in a second, get the rest of the equation written out, where this is the area moment of inertia defined by the water line. And the best way to describe this is to actually look at the example take a look at example 313 in the book, and I will produce another video on that if you're interested in looking at it. So now the only remaining thing that we need to do is use some trigonometry. So I'll remind you that x bar is equal to CC prime. So we can rewrite that equation as being CC prime equals the area moment of inertia tan alpha divided by the total displaced volume. So this was just the equation that we derived using the moment of inertia. But then we can also use a couple of simple trigonometric features from the figure above. And I'll write them down and then we'll go look at them. So C prime is just going to be equal to Cm times tan alpha. So you can see that Cm is just going to be equal to the moment of inertia over the volume. And the second thing that we need, remember we're interested in this metacentric height. So that equals Gm, and that's just equal to Cm minus Cg. So let's go back and look at the figure just to orient you as to what these things are. So we're looking again at this triangle in here, and we can see that this side, this is the angle alpha. It's a little hard to read there, but this is the angle alpha. So that the tan of alpha is going to be equal to the opposite side over the adjacent side. So tan alpha is going to be CC prime over Cm. So that was our first equation that said that CC prime, this side, was equal to tan alpha times Cm. The second thing that was said, it wasn't even a trigonometric identity, it was just a distance thing that said that Cm was equal to, Gm was equal to Cm minus Cg. So those are just some simple relationships that we can get from this figure. And we use those now to combine, we combine the equations. We note again that, that Cm is going to be equal to I over the area moment of inertia over the displaced volume. And so we can plug that in here. And what we end up with for our final equation for the metacentric height is that Gm is simply equal to this area moment of inertia divided by the total displaced volume minus the distance between the center of buoyancy and the center of gravity, which we can get from buoyancy. So, that is our final relationship that gives us the metacentric height, reminding us that, and here it is written down here at the bottom. And just to remind you that the stability conditions are that, go back here, this is the key point for this section, that if in fact Gm is positive, we have a stable situation. If it's negative, the ship is unstable. So we now have a means for calculating, go back here, we have a means for calculating the metacentric height, and we can do this in problems and determine stability. Okay, that's it for now. Thanks a lot, and that concludes section 3.7 and chapter 3.